Okay, hello, everyone. Welcome to today's colloquium session for TBS. We have as a speaker Erin Hayes. She's a PhD working with Casey Mandel, and she will tell us all about Gauss supernova. So take it away.
Yeah. Hi everyone. Firstly, thanks Priscilla for inviting me to give the colloquium. I'm excited to talk to you all today about strongly lensed supernovae and GausSN, our model for them. As Priscilla said, my name's Erin Hayes. I'm a PhD student at the Institute of Astronomy in Cambridge. And today I will be presenting GausSN, which is a new model that we've developed for Bayesian time delay estimation with strongly lensed supernovae. And importantly, this is work that's been done in collaboration with the people listed on the screen. So yes, and if you're interested in learning more about this work, we did put it out in the archive just a couple months ago now, so you can feel free to check out the paper at this archive link. Yeah. So just to give you a brief kind of outline of what this talk is going to go through, first I'm going to just give an overview of the Hubble tension and where we're at with the Hubble tension today, to motivate why we are interested in studying gravitationally lensed supernovae, or at least one of the reasons that we're interested in studying gravitationally lensed supernovae. After that, I'm going to go through the GausSN model for time delay estimation, and give a couple of examples of how GausSN performs on simulated data as well as a case kind of study of GausSN's performance on real data. And then I'm going to, just at the very end, give a little bit of prospects, future of time delay cosmography with lens supernovae, with a particular focus on how LSST is really going to help us build up exciting samples of lens supernovae. So yes, just to get into it. As many of you will be aware, there is currently a 5 sigma tension between early and late time estimates of the present day expansion rate of the universe, which is what we call H naught. The early time estimates of H naught come from the cosmic microwave background, or the CMB, and they use lambda CDM, or lambda cold dark matter, which is kind of our present best model of the universe, to estimate the expansion rate of the universe today based on these fluctuations in the early universe, so based on these fluctuations in the CMB. And so we're using this early time light in order to get our early time H naught estimate. On the other hand, we have the late time measurement of H naught, which comes from the local distance ladder. And as the name implies, the local distance ladder uses nearby objects or local objects in order to measure H naught. And the way that this H naught estimate works is that it links together multiple distance probes. So firstly, we typically use parallax to calibrate distances in the very nearby universe, and then link that together with Cepheids, which have a pretty well-defined period luminosity relation. And then we use the Cepheids to anchor the distance calibration for type 1a supernovae, which we can observe out to higher redshifts, and then get our H naught estimate out in the higher redshift universe. So because of this linking together of multiple calibration systems, the local distance ladder relies on precise luminosity distance calibration, and that can be subject to a couple of sources of systematics, which can ultimately bias our H naught estimate. But it's important that we do have this local probe of H naught, because it's a direct estimate of H naught, which means it's independent of any model of the universe. So while the early time estimate gives us is contingent on lambda CDM, the local distance estimate gives us a model independent kind of cross check of our model of the universe. And so as you can see illustrated in this plot, which shows some indirect estimates of H naught from the early time light, and direct estimates of H naught from late time distance ladder type estimates, you can really see clearly that there is this tension between the two estimates, where the red band shows kind of the best estimate from the CMB as of a couple of years ago now. And then the blue estimate shows kind of one of the more recent estimates of H naught from the local distance ladder SHOES team. And so you can see that the tension is becoming pretty significant. And that is an issue for lambda CDM if it's found to be if it's a physical cause of this tension. And if we focus more on the direct side, which is the side that I work on as a supernova person, you'll see here in these green points, these are the points, observations or measurements of H naught that use Cepheids as the distance calibrators. But there's also a different way of calibrating the distance ladder. So rather than using Cepheids, it uses this method called tip of the red giant branch, which is based on, we know pretty well how bright and massive stars can get on the main sequence before they end up evolving off of the main sequence. And so if we can leverage kind of some of that information, we can calibrate distances to these objects that should have known luminosities. And you can see that some of these measurements do inch closer to the CMB estimate. So there is some uncertainty on the direct estimate side as to whether, is calibration an issue in our estimates, or is this really an issue with the physics that's underlying all of these things? So yeah, the open kind of question on the direct estimate side of H naught is we need a new local probe of H naught that is independent of the distance ladder in order to cross-check our local H naught estimate, so that we can really be sure that that our distance calibration is doing what we want it to do. And so that brings me to why we are interested in studying gravitationally lensed supernovae. So just to give you a little bit of a refresher on what gravitationally lensed supernovae are, they're when a background supernova is strongly lensed by a foreground galaxy or galaxy cluster, and the foreground lens bends the light of the background source, or the background supernova, so that the supernova appears as multiple images. And because the light from each of these images travels along a different path, the images are going to appear with some time delay relative to one another. And that's because of the differing lengths of these paths. And so these systems have some information about how long it takes for light to travel along paths of different lengths, which we can leverage in order to measure H naught. And importantly, I want to point out that this is a one-step distance estimate. So we're not dependent on the distance ladder calibration here. We're not getting what's known as a luminosity distance to the background supernova, which would be based on the brightness, which is calibrated on other rungs of the ladder. But instead, this is what's called a time delay distance, because it's using the kind of physics encoded in these systems differently. So what are the ingredients that we need to get an H naught estimate? There are three kind of key ingredients, one of which I've already alluded to. That's the time delay, which I'll call delta T or just delta. And that's the delay in appearance of one image relative to another in these systems. The next ingredient that we have is what's known as the lensing potential. And this tells us the path length traveled by the lensed image light. And it's based on the gravitational potential of the mass distribution of the lens. And finally, these two things are combined into what's known as a time delay distance, or d delta t, and this is the distance traveled by delayed image light. And importantly, we know that distances are proportional to H naught, so that is how we can get our constraint on H naught. So to summarize, if we look at how long the paths are and the differences in time it took for the light to travel along these different paths, we can work out a cosmological distance that the light has traveled, which can then be used to constrain H naught. And I'm going to point out here that the d delta t, the time delay distance, is actually proportional to the distance to the deflector, or the distance to the lens, the distance to the source, and the distance between those two, which means that we're only weakly dependent on other cosmological parameters. We're not getting much constraining power on the different kind of mass fractions and things. So we're not sensitive to a cosmological model here. Those things roughly cancel out. because of this ratio of distances. So we're only sensitive to H0, which gives us the direct probe. This idea dates back to 1964. So this kind of seminal paper by Refstall was the first to recommend that this method be used in order to estimate H0. But there have been kind of a couple of complicating factors. The first is that we need a very specific geometry in order to observe multiple images of a strongly lensed supernova. Already, yeah, clusters, supernovae are already rare and very short-lived. And so getting the short-lived supernova, finding that in time in this kind of system where you have multiple images, has made this really difficult to date. But fortunately, in 2014 was the discovery of the first resolved multiple image gravitationally lensed supernova. This was found in real time by Pat Kelly's team in Hubble Space Telescope HST data. So this was really an exciting moment for lens supernova cosmography. And you can see here is the image of supernova Refstall. In this red circle are the 4 images that were originally found, which were produced by lensing by a galaxy scale lens. So that's this galaxy in the middle here, caused the appearance of these 4 multiple images. And this system was actually very cool because it was also in a cluster lens field. So this host galaxy was imaged 2 other times that you can see circled here. So there was an image of supernova Refstall in this galaxy in the 1990s, they expected, and in this galaxy, it was predicted for a 5th image to appear, and that did in fact happen. So this was a super cool discovery, which I will talk about a little bit more in detail later in the talk. But since the discovery of supernova Refstall, there have been kind of this growing rate of finding lens supernovae. So supernova Requiem came pretty quickly after Refstall, and then supernova Zwicky, for example, was the first lens supernova that ZTF found. And more recently, supernova Hope was discovered in JWST data. And this is not a comprehensive list of the number of the lens supernova that we found. So we've really done, we've been getting a lot better at finding these objects, which is exciting, given the cool kind of cosmological and also astrophysical applications of these systems. And of course, here's, my the slide that we always see about next generation cosmological surveys. So the Rubin Observatory, of course, and also the Roman Space Telescope are expected to increase our sample of discovered lens supernovae to tens to hundreds of objects. So this is going to be a really cool sample to do cosmology with in the next decade. But of course, in order to best take advantage of this data, we need strong statistical methods for estimating the necessary ingredients in our H0 estimate. And in particular, I'm going to be focusing today on how we estimate our time delays from these systems. So that's one of our 3 key ingredients. That brings me to the GausSN model for time delay estimation. So GausSN is a Bayesian Gaussian process approach for time delay estimation. Gaussian processes are a distribution over functions such that the probability distribution of any finite sample, f of t, from the Gaussian process is a multivariate Gaussian. And so the multivariate normal is described by a mean function and a kernel, which are defined by some hyperparameters that control, for example, the amplitude of the fluctuations that you get and the timescales of those fluctuations in the functions drawn from some distribution, from this distribution over functions. So you have a mean function and a kernel that determine the properties of the distribution of functions which you're drawing from. I'm going to point out here that GPs have become popular in time domain astronomy because they have a lot of cool properties, including kind kind of filling in sparse data. So they become particularly popular in the classification world for extrapolating between sparsely sampled data points in order to fill in light curves so that you can feed that into a neural network, for example, and like a grid of time and at a grid of times. In this case, we're not interested in using the Gaussian process to extrapolate between data, but we're going to marginalize over the true shape of the underlying light curve and instead, and also extract some defining hyperparameters of the system. And where those hyperparameters are, for example, the amplitude and the time scale. And so what we want to do is encode some physics into our covariance function or our kernel here in order to essentially put in the time delay as a hyperparameter in this system in order to be able to sample that to get an estimate on the time delay for these systems. And so what is the physics that we want to put into our covariance function? Well, we know that when we look at the light curves of, we'll say we're looking at this image 1 and image 2, for example, of this lens type 1A, oops. This is, we're typically looking at the light curves, the plot of flux over time, and we expect both image 1 and image 2 to appear with some overall magnification relative to the unlensed flux of the type 1A. This, of course, is just for demonstration's sake, it's not real data. And we don't necessarily expect the overall magnification to be the same for both images due to asymmetries in the system. In this model, we're only going to be sensitive to the relative magnification between the two images, so we don't have any constraining power on how much the light curve is magnified overall, but instead we're just focusing on the relative magnification of image 2 relative to image 1. We also expect the image 2 to appear with some time delay relative to image 1. And so that's kind of the other bit of physics that we want to encode. So we can define our covariance function, this k here, such that it depends on the lensing parameters, which are the time delay, delta t, and the relative magnification, beta. And that's going to enforce some correlation between the images as expected from our physical understanding of the system. So that means that we're modeling the multiple images as copies of the same underlying light curve. So by defining our model in this way, we can sample a joint posterior over the lensing parameters and the GP hyperparameters. So that's going to be, again, the amplitude and length scale, while marginalizing over the exact shape of the light curve. So we're not defining just one parametric curve that describes the data, but we're thinking of the underlying light curve, which we know is the same for both images, as a draw from this distribution of flexible non-parametric functions while marginalizing over its true shape. I'm going to complicate the picture a little bit more because there's some additional factors that we need to take into account here. One of the main ones is microlensing. So microlensing is caused when there are stars and other dark compact substructures in the foreground lens. And because as the supernova expands, because of the small scale of these structures, as the supernova expands, it can pass behind additional structure. And so this figure illustrates how one image A here, might be additionally lensed by a star in the galaxy, causing it to appear brighter than the other images. And this is something that can vary in time. So rather than just one overall magnification or one relative magnification, we're seeing this time varying lensing or magnification contribution. And I'll point out also that this can make objects brighter or dimmer, depending on, where the supernova exploded relative to kind of the masses in the foreground. So again, rather than just this constant magnification, I'm going to introduce in the image 2 light curve a kind of the supernova passing behind a star at around t equals 8 days. And that causes this kind of artificial shift in the apparent peak of the light curve. And so you can imagine this can lead to some uncertainty in your time delay estimate and can bias your time delay estimate if you don't account for the possibility of this time varying magnification term. And so practically, this is implemented by expanding just our constant magnification term, relative magnification term beta into beta of t. So that relative magnification now becomes a function of time. So there's going to be two different models that I consider for the microlensing in future work that I'll present, and that is the constant magnification model, which just treats the magnification as a constant in time. So it's just kind of the baseline, simplest model. And then we also are going to treat microlensing as a sigmoid function. So yes, that was motivated by looking at realistic microlensing simulations. So you can see in this plot some realistic microlensing simulations from this Foxley-Marable 2018 paper. And you can see that a lot of these curves kind of roughly look like a sigmoid function. And then on the right here, you can see draws from our sigmoid magnification, which roughly approximate kind of some of the behavior that you see here. Of course, the sigmoid is not going to be as flexible as is not going to be able to capture all of the variation in the real microlensing simulations, but it's at least a jumping off point for kind of incorporating some sort of time varying magnification term. So now, instead of having, we can have just our time delay and overall relative magnification, but then we can also include these time varying magnification terms if we choose to include some microlensing model. So to summarize the kind of key points of the GausSN model, we are modeling the light curve of any supernova type as a draw from a Gaussian process, and we are independent of templates and spectroscopy. So the other kind of leading methods for time delay estimation use templates to estimate time delays, but there are a couple of open questions in kind of firstly the redshift evolution of these templates. So as LSST and other future surveys are going to probe higher redshifts, and lensing actually lets us see higher redshift supernovae, there might be some systematics that arise from a redshift dependence in the supernova light curve shapes. And so we aren't sensitive to that because we are not using templates. And also spectroscopy is not necessarily going to be available for all of the objects that LSST or other future surveys find. And so we don't need to, we are not dependent on spectroscopy for either confirming the supernova type so that you know which template to use, or when you are using a template, shifting that from the rest frame into the observer frame. We don't need to know any spectroscopy information about these systems. The GausSN model also fits any number of images in any number of bands simultaneously. It treats macro and microlensing together alongside time delay estimation. And again, that's important just so that we marginalize over that possibility together, so that we are getting appropriate uncertainties on our time delays. And it's a fully Bayesian treatment of the system parameters. So you can sample the posteriors using MCMC or nested sampling. In all the following examples, I'm going to use nested sampling because it tends to be good at handling multimodal priors or posteriors, which we typically end up with. But there's also MCMC algorithms that are built in as well. But all of that's great. I need to convince you still that this method works and works well. So I'm going to test firstly on these Arenze et al. 2024 simulations. So these are simulations of type 1a lens supernovae that emulate the cadence and depth of expected Rubin-LSST data. They have realistic time delay and magnification distributions and a realistic microlensing treatment, which is based on kind of up-to-date models on the explosion mechanisms of type 1a. So you're getting really realistic, high-quality microlensing simulations from these. And so I'm going to first show the results on the individual object scale. So you can see in this plot, you have the fitted light curves. The blue curves fit image 1, and the red curves fit image 2. But importantly, I want to highlight that the red curve is actually an exact copy of the blue curve, but which has been shifted in time and magnified, or in this case, demagnified, in order to match image 2. And this blue curve has been conditioned on all of the available data. So yeah, we sample something from the posterior, sample the time delay and magnification from the posterior, shift the image to back in time and magnify it, and then condition the full light curve and make 2 copies of that to fit each of the images. And you can see that there's yeah, it's a pretty nice fit to the data, so that's promising. And this is a relatively long time delay of about 67 days. So we're able to measure the time delay to 2% precision. And I'll point out that if we were able to measure the lensing potential perfectly, which is, of course, a big assumption because that's not an easy estimate to do. But if we were able to do that perfectly, a 2% precision estimate on the time delay would lead to a 2% precision estimate on H naught. So even with just this kind of sparsely sampled light curve, we're able to get pretty good precision, which, yeah, is great for our prospects for measuring H naught. And then here are the results for the sigmoid. Oh, I'll point out one other thing, which is that the true time delay is actually slightly outside of the 1 sigma region here, not concerningly so, but just to point that out, when we include the possibility of microlensing through this sigmoid magnification model, we actually include now the truth within the 1 sigma confidence interval, just as a kind of little note on why it's important to account for the possibility of microlensing. You can see again here the fitted curves, and now the bottom panel shows the relative magnification as a function of time, and you can see there's not really doesn't really look like there's microlensing in this curve, but there is kind of some spread still that you see here, which again just emphasizes that we do need to account for the possibility of microlensing. Of course, now our precision is slightly increased, but still we're able to measure this time delay to 6% precision with only LSST data. This is just what we get out of LSST, assuming no follow-up from any other telescopes. So yeah, this is really promising. On a population level, we also have exciting results. So on the left here, I show the fit minus true time delay for the constant magnification model, which is shown in blue, and the sigmoid magnification model, which is shown in red. And we measure between about 25% of the time delays within 1 day and 50 to 60% of the time delays within 3 days. So yeah, we're doing a really good job getting close to the truth. And then in the right panel, I show the CDF of that same distribution, but scaled now by the uncertainty on the time delay. And so we want this to kind of roughly mimic a normal distribution, because if we're getting, the truth within the 1 sigma confidence interval 68% of the time, then that means our error bars are well calibrated, and we are nearly hitting that benchmark. So it's closer for the sigmoid model because, again, if we're marginalizing over the possibility of microlensing, which we know is a possibility, then we are getting closer, getting better calibrated uncertainties. But really, overall, it's doing pretty good. But something that I pointed out earlier was that this is agnostic to supernova type, and these simulations are only for 1As. But I really do want to demonstrate that this does work regardless of the supernova type that you're looking at, and not just for kind of the well-understood 1As. So I also have some simulations, which I did as part of this paper of type 1As, 1Bs, 1Cs, 2Bs, 2Ns, and 2Ps using templates from the SN Cosmo package, which also emulate the cadence and depth expected from Rubin-LSST, but do not have any microlensing contribution. So this means that these objects are simulated from the constant magnification model, and then we're going to fit them with the constant magnification model as well as the sigmoid magnification model, which gives us a sense of, okay, if we assume the right model, do we do a good job? And if we assume a wrong model, how does that affect our results? And so I'm going to show here the results broken down by subtype of supernova. And you can see, yeah, that for, again, this top row is showing the fit minus true time delay. And you can see that we're getting between 30 and 40% within 1 day. And again, yeah, 55 and 50, yeah, and 70% within 3 days. And that's pretty consistent regardless of supernova types. You can see the distributions all look pretty consistent across here. And then for the kind of scaled distributions, again, we're getting actually the results are a little bit worsened here, which I have some thoughts on why that is. So if you're curious about these results, I'm happy to kind of speculate a little bit more there. But again, we're getting pretty good results that are at least consistent across all the supernova types, maybe with some exceptions. For example, these two Ps, which I also have some thoughts on. But yeah, this is kind of matches the standard that the current template-based approach is kind of set, and so we're pretty happy with this performance. So to conclude about the GausSN model, the GausSN provides competitive time delay estimates that have fully Bayesian uncertainties, are not sensitive to fine-tuning, and make minimal assumptions about the underlying light curve shape, therefore minimizes our sources of systematic uncertainties. We treat macro and microlensing together in a novel and robust way with a modular implementation for easy testing of other parameterizations. And it's scalable given current projections of lens supernova discovery rates from current and upcoming telescopes. But all of that was on simulated data. Let's get into kind of a case study of supernova Ruffstall and see some results on real data. So as I mentioned, supernova Ruffstall had 4 images, which were the first 4 to be discovered, which were produced from a galaxy scale lens. These images were discovered in HST imaging in real time, but the time delays of these 4 images were too short to get a competitive H-naught constraint. Yeah, but fortunately, there was a predicted 5th image that was expected to appear about a year later from cluster scale lensing. And fortunately, it did appear just under a year, and we were able to catch it. And so here are the light curves from supernova Ruffstall, where the pink, blue, green, and yellow are the first 4 images. And the purple one is what's known as image X, which is the 5th image that we were able to catch pretty well when it reappeared, or when it appeared, I guess the 5th image did. Unfortunately, it was pretty demagnified, but still there was, because of the long baseline of the time delay of a year, this was this was kind of our first opportunity to do an H-naught estimate from a lens supernova. And so I show here the posteriors for the GausSN fits in blue. So you can see in this plot, or yeah, in kind of every other row, the time delay of image 2, 3, 4, and image X or image 5 relative to image 1. So the blue shows the posterior from GausSN, and then the red solid line and the red shaded region show the estimate and 1 sigma confidence interval from the Kelly 2023 paper that did the first H-naught analysis of supernova Ruffstall. And so there's, 2 happy things about this. We're in very good agreement on all of the time delays, including for the kind of most cosmologically interesting time delay of image 5. And so that's reassuring that the Kelly paper knew what they were doing, and also that our model is now doing a good job. So we were pleased with that. I'll also point out that the relative magnification, I show the truth, which you can see for a couple of the images, but I don't show the 1 sigma confidence interval because it actually covers the full range of all of the GausSN posterior spaces that are shown here. So for the relative magnification as well, there is, good agreement with the Kelly estimates. And so, of course, the Kelly paper did take this to an H-naught estimate. And so the kind of main science result is then summarized in this figure, where you can see the Ruffstall results are shown in this orange and green, orange and blue, estimates here. And then that is compared to the Planck estimate, which is shown as a gray dashed posterior here or down here. And then also to the shoes H-naught estimate from the local distance ladder, which is shown in this kind of brownish color here. And so supernova rough stall is in very good agreement with the Planck value. It's a little bit off from the Schu's value, but there is still some posterior density there, so we can't, this isn't a decisive measurement, but at least it is it is an interesting evidence, I guess, which will contribute to this kind of discussion on the Hubble tension. So yes, that's kind of the first H0 estimate that's now been done with lens supernova. But of course, I also said that I would talk a bit more about the future of time delay cosmography. So just in the past year, there's been the discovery of supernova Hope, which I mentioned before. It was discovered a year ago in March 2023 by JWST. And then more recently, supernova Encore was discovered in December of last year, also by JWST. And so again, as I mentioned before, we're getting much better at discovering these objects. And we expect a new H0 estimate from Supernova Hope. It should be out very soon. I know that, so that it'll be interesting to see kind of as we get additional data points from these systems, how that fills in this picture of the Hubble tension. And then, of course, we have the future, which will be largely influenced by Rubin-LSST. And I'm going to talk a little bit about some work from Nikki Arenze, which she put out late last year. And she predicted that Rubin-LSST was going to observe around 44 lens type 1a supernovae per year. So this is not even all the supernovae that we're going to find that are lensed in a year, but just the type 1a's. And 44 is almost one a week. So that will be in our Rubin data. So this is really exciting. You can see here a plot of the number of lens supernovae that are lens 1a's that are discovered as a function of how many observations there are of each object. And so this is broken down into two possibilities, which are based on the two different survey strategies. So for example, we use a non-rolling strategy versus a rolling strategy, how that affects kind of the types of lens supernovae we're going to discover. But yeah, the main result being that we're going to discover between 40 and 50 lens type 1a supernovae a year. So that's really going to be an exciting sample that we get to work with. And more than that, there's going to be this kind of gold sample that she defines, which are bright. So as you can see here, this shows the peak I-band magnitude. And so if we look in the non-shaded region, that kind of defines this gold sample. There's actually two different types of configurations that you can expect to see based on the gravitational lensing. So the first is two images that you see, and those are called our doubles. Our four images, the Einstein cross, which is the pretty classic one that you think of. That's the quads, are our four images. And so you can see here, there's this going to be the sample of bright, well observed. So this is the number of observations there are before maximum of before the peak of the light of the supernova. And also with longer time delays, which give us a good baseline for our H0 estimate. And yeah, we're expecting a gold sample of around 10 type 1a supernovae per year, which have these kind of ideal properties for estimating H0. And that means that the goal of measuring H0 to kind of this percent level precision with gravitationally lensed supernovae is within reach with Rubin-LSST by only year 3. So if we can do a good job finding these objects, it's going to be possible to measure H0 well within just the first years of Rubin-LSST. So that's a very exciting prospect. And with that, I will leave you with this kind of optimistic note of we're expecting an exciting next decade for lens supernova cosmography, given the exciting prospects of Rubin-LSST, and then also I'll shout out the Roman Space Telescope as well, which will be really exciting for probing even higher redshift ranges than LSST with this. But with that, I'll say thank you. And again, if you're interested in learning more, you can feel free to check out our paper. Yeah, thanks.
Thank you so much, Erin, for the amazing talk.